Well, good evening. I'd like to welcome you all here to the Baker Institute. This event tonight is actually sponsored by the Baker Institute and the Space Institute, and I'd like to introduce Pat Reif, who's going to say a few words about the Space Institute.
Thanks very much. It's always wonderful to have all you all here this evening. The Baker Institute and the Rice Space Institute have had a very cozy relationship ever since they were both founded about the same time, and including working on the World Space Congress here in town a few years ago. It gives me great pleasure to co-sponsor this event, to hear some of the really exciting things from Mars. Now looking at the rocks and how that relates to the search for life on other planets. If those of you who are here that are already members of the Rice Space Institute Associates, glad to have you here. If you are here and you are not members, let me know, or go to our webpage space.rice.edu and click on join, and we'll send you email invitations for other future events. For example, we will have a public observing at the Rice Telescope facility near entrance 13 this Friday night, right before graduation. In fact, we'll have observing the stars in and amongst the fireworks that will go off at 10 o'clock. So that'll be interesting. It'll always be fun looking at the shooting stars, and some of them are fireworks. But anyway, I really appreciate you all coming, and I hope to see you at future events. Thanks.
Thank you, Pat. Well, here in Houston, we're very fortunate to have the Johnson Space Center in close proximity, and of course, you hear a lot about human exploration, which is the focus of activities out at the Johnson Space Center. But there is also a group of very excellent scientists that get involved in the activities at the center, and they get involved in and are still involved in the lunar sample program and a lot of planetary science. And they don't get a lot of the publicity that the human spaceflight activities get at the center, but it's nonetheless a very important part of it. And back in '96, this group, under David McKay and Everett Gibson, made a very significant discovery that really, I think, has put a greater focus on Mars and the exploration of Mars. And tonight we're going to hear about that. And I'd like to introduce Neil Lane, a senior fellow in science and technology, who's also involved in space activities here at the Institute, and of course was a science advisor to President Clinton. I'll turn it over to Neil.
Thank you, George. I mean, my involvement in space activities is to hang around with George Abbey, who's kind of Mr. Space, and it's a great pleasure to work with George. We are very, very fortunate here to have George associated with the Institute, and Israel Govan back here keeps us out of or into mischief. I mean, you know who know Israel know that he's a key element in the space activity, working on the private sector side, but a very good friend and strong supporter of NASA and the whole Houston region involvement in space. It's a great honor for me this evening, to be able to introduce our speakers, David McKay and Everett Gibson. They're both distinguished scientists at the Johnson Space Center. Everett and David are famous within the science community for extraordinary careers of scientific investigation, including hundreds of publications and citations. They are also known in the larger public for this incredible work of the Johnson Space Center Mars Meteorite Research Team that announced in August of 1996 the discovery of what they call possible signatures of past biological activity on the planet Mars. They made this discovery by studying a meteorite, which we all fondly know as ALH 84001, or I think that's roughly what it is. It came to Earth from Mars. We know that because of the investigations of the makeup of this meteorite, which are characterized in such a way that it really could not have come from any place else. And this meteorite was knocked off Mars by a collision, which I don't think we had a chance to observe, with an asteroid sometime in the past. And I was particularly interested in this meteorite because it came from the Antarctic. where I hung out from time to time in my National Science Foundation days. I visited there 3 times. I froze 3 times. I never quite got to Allen Hills, which is where these meteorites collect, and it's one of the colder areas, and I think windier areas on the continent. But it's very special for delivering a number of meteorites, not all of them, but a number of meteorites, and this is a very famous one right now. I also recall very clearly the NASA press conference in Washington, where these results that George referred to and I just mentioned were announced to the world. I sat next to Bruce Alberts, president of the National Academy of Sciences, at that event. Apparently our images are captured in some photograph. I hope we didn't mess it up. I know that Bruce and I agreed it was a special day for science, unlike any day that we had experienced, and President Clinton was quoted as saying that he found the discovery stunning. Well, I can tell you it takes a lot to stun the occupant of the Oval Office in any administration. As you can imagine, the announcement was controversial. I think the debate continues to this day, but we'll get an update on that. And since the biographical information on Drs. McKay and Gibson was circulated, I'll be very brief with the introductions now. Dr. Everett Gibson, a 35-year veteran with NASA, is a senior scientist, geochemist in the Astro Materials Research and Exploration Sciences Office of NASA's Johnson Space Center. Currently, he's a PI in NASA's exobiology program, looking at the geochemistry of Martian materials, as well as a key scientist on the European Space Agency's Mars Express Beagle 2 mission to Mars, and we'll hear something about that this evening. Dr. David McKay, who joined NASA in 1965, is chief scientist of astrobiology at Johnson Space Center. He was first author of the famous 1996 science paper announcing the discovery I mentioned a few minutes ago. At NASA, David cut his teeth, so to speak, on moon rocks and on teaching geology to Apollo astronauts, and currently he's a PI on both the Mars Meteorite Program and the Lunar Rocks Program. David's one of ours, having 2 Rice degrees, I'm proud to say. Both our speakers, I've said before, have published widely and received international recognition, many honors for their work and their extraordinary careers. We're delighted they've taken time to talk with us this evening, and so in some order or together, please welcome David McKay and Everett Gibson.
Thank you very much, Neil. We're going to have a bit of a tag team match here today, so bear with us a bit as we go. I'm going to start off here, and I'm going to give you an update on the meteorite studies. And then when I'm through with that, Everett will tell you about what's going on Mars and the missions and what the Europeans are doing. So we're going to go from little tiny things to great big things here. But I'll start with a very interesting place, which is Antarctica. This is where the story begins. This is where the meteorite was found. This is where a lot of meteorites are found of all kinds, not just Mars meteorites. And why is that? Well, meteorites fall all over the Earth in a fairly random pattern. Most of them go into the ocean, but the ones that fall in Antarctica are nice because they fall into the ice. There are not a lot of other rocks in the ice, and the ice moves along. When it reaches an obstruction like a mountain, the ice tends to go up, and we have meteorites that are stranded on the surface. And so as we walk around on the surface, we find these meteorites. Now, I've not been there, but Everett's been there, and thank you. This is just sitting on the surface of the ice. And it's probably been there maybe a year or so. These meteorites spend most of their time buried under the ice, but they come out on the surface. And there are 2 NASA NSF teams that go down every year and look for these. Plus, there's a Japanese team. And They don't clean it out because there are new ones that are brought up every year. So it's kind of a unending supply. This was what happened in 1984. This is a meteorite that was found here, and it turned out to be Allen Hills 84001. And this meteorite, it turns out, was misidentified as part of an asteroid for many years, and it wasn't until from 1984 when it was first found to 1993 is when it was identified as a true Mars meteorite. A number of people studied this, and there's a lot of data on it. And if you put together all the publications and the stories, here's what happened. 4.5 billion years ago, the meteorite was formed in the crust, upper crust of Mars. About 4 billion years ago, Mars was fairly active. There was certainly water on the surface. Some of that water soaked into the ground and got into the meteorite. A little bit got into the meteorite, forming some features that I'll talk about. And then it sat there pretty much undisturbed for a long time. And then 16 million years ago, an impact, an asteroid or a comet hit Mars, blasted this meteorite off. The meteorite traveled around the sun for 16 million years, and many meteorites do that when they're blasted off planets, and most of them either go into the sun or they go out and they escape from the solar system. A few are attracted by the Earth's gravity, and this one is known to have fallen into Antarctica 13,000 years ago. Now, we studied this. We were not the first to study it, but we were the first ones to essentially interpret the data in terms of possible evidence for life. And what we found was that there are carbonate globules in it. Can we turn the lights down a little bit more? There are carbonate globules in here, which I'll talk about in more detail. And we interpreted that they could have been formed by microbial activity. But in any case, they were evidence of low temperature liquid water. We found really the first detailed report of Martian organic compounds in the meteorite, the polycyclic aromatic hydrocarbons. To be fair, an English group had discovered organics before in another Mars meteorite, Wright and company, but ours was the first real specific report. And then we found remnants of organisms present as biominerals. I'll talk about those. And then one of the most controversial part of it, we found features that appeared to be possible fossilized organisms. This is the press conference that Neil alluded to when we first announced our results in 1996. This was held at NASA headquarters. And I'm not sure that I see Neil in that picture, but there's Everett Gibson, and I think there's me. There's The Rock. This is Wes Huntress, who was head of the science group at NASA. That's Bill Shopp. And I'm not sure who else we have there. It was a real zoo. There were like 35 TV cameras and maybe 100 still cameras. And it was a real circus. Not the best way to do science. But it did have an effect, kind of an unintended effect, of really capturing the fancy of both Congress and the public, and it caused an awful lot of attention, and we've been told by Dan Golden, the former head of NASA, and some others, that it essentially was worth $6 billion to NASA over several years. Not that NASA got that much more, but it prevented the decline of NASA's budget by that much. And several people have told me that NASA's budget would have gone down without the excitement of the meteorite. It caused a lot of stir in the public. We collected some cartoons from that time, and maybe a couple dozen cartoons all over the country. Well, where are we now? We have 35 known meteorites. At the time that meteorite was found, there were, 6 or 7 meteorites known to be from Mars. We now have 35 of them. That's just incredible. Maybe half of them are from Antarctica and half of them are from elsewhere. Other places include the desert of North Africa, Australia. But Antarctic meteorites are the best because they're the most pristine and the least weathered in general. Now, how do we know these guys are from Mars? That's really that's a question that people often ask. It's a result of studying this meteorite that you see on the table, EETA 7901. That's a picture of it there. That's a picture of one of those faces there, I think after some of it was split off. This meteorite was analyzed by Don Bogard of the Johnson Space Center in his rare gas analysis laboratory. And what did he find? He found that the gases that were trapped in those little black areas, which are mainly glass, those gases matched more or less exactly the gases measured by Viking, which landed there in 1976. Over essentially 8 orders of magnitude, the gases matched up perfectly. And it is very difficult to argue against this rock coming from Mars because of that match. Since that time, of the 35 meteorites, about 22 of them have also been found to have gases which match the Mars atmosphere. Now, in addition to that, how do we know some other ones that don't have gases in them are from Mars? Well, we use oxygen isotope analysis. The ratio of oxygen 18 to oxygen 16 and the 17 to 16 ratio. And it turns out there are a number of trends that become apparent, and we're going to zero in on this trend here. Also notice this trend labeled TFL. All rocks from Earth are on that trend. Moon also. But if you switch now, if you magnify part of that, these are the Mars rocks here, or at least a subset of them, and they're quite distinct from Earth rocks and from other meteorites. So it turns out that Mars has a very distinctive oxygen isotope fingerprint. It is so distinctive that one careful oxygen analysis is enough to certify any rock is from Mars or not. And so that is really the gold standard now for telling Mars meteorites. Now, in studying these meteorites, we've noticed, we weren't the first to notice this, but we have perhaps been more interested in this than any other research group. We've noticed that these rocks, although they are all basalts, they are all igneous rocks, they also mostly have cracks in them, which formed on Mars and which got exposed to water on Mars, and that it is these cracks where we think we see possible evidence for life. And I'll tell you about that in more detail. But the point is, when we first said this, when we first talked about fossils in an igneous rock, a basalt, people thought we were just absolutely crazy because nobody looks in lavas for fossils. That's crazy. But it turns out that these rocks are full of these little tiny cracks, and there are all kinds of things going on in these cracks. All right, Allen Hills, one of the first things that we noticed was the abundance of these little circle things. Like they look like targets. They're really pancake shaped or coin shaped, and these are the carbonate globules. This is a carbonate here surrounded by a black rim and a white rim and a black rim. We sometimes call these Oreo cookies. And what is that material made out of? Well, it's made out of calcium carbonate, magnesium carbonate, iron carbonate in various proportions. And if you look at the chemistry of it, you can make a chemical map, and you can see that a typical one has a core of calcium and manganese. And then look at this rim. This is sulfur here, and this is iron. There's a rim of iron-rich and sulfur-rich material, which is the black part of the Oreo cookies. And then there's a big band here of magnesium, almost pure magnesium carbonate, sandwiched between that rim. Very strange composition. And I'll get back to that, but that had to be explained somehow. There's another feature of these that is really fascinating. If you look at these carefully, these little carbonate pancakes, you find that they're not just sitting on a fracture surface, but they're actually embedded in the surface. Something has made a hole, and these little carbonate globules or pancakes are down in the hole. And this is almost always true. Not always, but mostly true. And so they're thin, they're shaped like a coin, and they're in a little pit here. Now, how do you explain that? And we're not sure, but there are a lot of explanations that other people have come up with that won't explain that at all. Our explanation is that the pit was actually etched out by microbial activity generating organic acids which ate into the rock from a microbial colony, and then at that point the microbes more or less catalyzed the crystallization of the carbonates, which grew and filled up the hole or the pit. That's a working hypothesis. We have yet to prove that, but we're working on it. We do, yeah. There are microbes that eat into silicate rocks. There are microbes that eat into shales and basalts both. And you can see etch pits developing on Earth. Another feature of these carbonates is that they have clay minerals. This is smectite, which is a water-containing clay mineral. Now, when people started to study this, they claimed that these things were formed at high temperatures from a melt, because there was no obvious water involved. And so we and other groups now have found these clay minerals which do contain water, and which, if you heat, lose their structure. So the presence of these, and sometimes in the very bottom of those pits, indicates that there was water present when those pits were formed and when the carbonates were formed. Now, I talked earlier about the cracks. I want to talk a little bit more about the cracks. Many of these meteorites have cracks in them. How do we know that those cracks formed on Mars and not the Earth? Well, because this is a fusion crust. When a meteorite goes through the atmosphere, it heats. It gets very hot on the outside only. In half a millimeter or so, it stays cold, but the outside heats up. So what happens if there's a crack here, and there's something in that crack, such as clay minerals, that crack heats up, the clay minerals decompose, they bubble, and they get sealed off by this now glassy fusion crust. So as soon as you see a crack being intersected by this fusion crust, you're absolutely certain that crack was there already. That crack is formed on Mars. Here's an example of some cracks in one of these meteorites, Nakhla, which is from Egypt. And these cracks are filling up with secondary material, which consists of clay minerals and carbonates and some amorphous silica. In places, they're long, narrow pits which have been carved into the olivine in this case, and then these pits are filled with various secondary minerals. Well, what's going on here? This is some kind of weathering by water at low temperature, relatively low temperatures. We don't know that biology is involved, but we do know that this is a low temperature aqueous process. Notice how jagged some of these get to be. Well, people on Earth have studied similar features in basaltic glass from the ocean floor, and they see that there are jagged intrusions into the glass from cracks. Well, it turns out in this case, these people have shown that these are caused by microbes. They have found DNA in these little tunnels that have burrowed into the glass. Now, we're not expecting to find DNA in the Mars meteorite simply because DNA is not stable over hundreds of millions or billions of years, but we are actively looking to see if in the Mars meteorite there may be some organic substance residue of microbes. We don't know that there will be or not, but we're looking for it. Also in these cracks, in addition to the clays and the carbonates I talked about, there are other interesting things. This is salt. This is ordinary salt, but it is not nice little crystals of salt like you get in your salt shaker. These are smooth plates of salt, and the reason they're smooth is that they were once filling up this crack, and then the upper part of the crack is busted away. This is calcium sulfate or gypsum underneath the crack, underneath the salt in the crack. These cracks can have very complicated stratigraphy. Here's another crack that is filled with calcium sulfate or gypsum. This crack shows that not only is there complicated stratigraphy, but there are time sequences here. This is clay mineral and carbonate, which once filled a crack. Then that whole crack was cracked again and filled with gypsum. Gypsum, by the way, is something that the robotic mission has recently found on Mars, and Everett will talk about that later. All right, summarize what we find in these cracks. These cracks are very interesting. They're clays, they're carbonates, sulfates. Again, we found all these sulfates, and they're also present in the Mars mission analyses. Halide or sodium chloride, and then some of these others we also found. So there's quite a range of secondary minerals. Now, one of the things that one of the unintended consequences of this range of minerals is that there's also a lot of different redox states present, different charges on these cations. Iron, for example, is normally +2 in the rock, but in these secondary phases, a lot of it's +3. Well, so what? Well, the so what is that this is a good energy source for microbes. There are many microbes on Earth that make a living by these redox reactions. In other words, when +2 iron is converted to +3 iron in the environment, there are microbes that tag along and get their energy from that reaction. Same thing going the other way, from 3 to 2. There are many microbes on Earth that don't require sunlight that live from these chemical reactions. And we we can't show that that's true so far on Mars, but what we're showing is that the chemical engine is there to provide energy. All right, to summarize, what do all these cracks have to do with life? Well, we've seen that they show us that water was there, liquid water. We've seen there's an energy source. We know there's sunlight on Mars, but we also have seen for the first time there's chemical energy. And in the cracks, there's certainly some space to grow. We'll get to the organic material in a minute. All right, what else is in the cracks? Well, here's Nakhla, and this is a chip of Nakhla showing a crack, and part of this upper layer is busted away here. And what do we have? We have a very bumpy surface of rounded materials. We're proposing that this is essentially a colony of fossilized microbes on this surface and even on the underside of this cliff here. These things we're proposing actually grew in the cracks. Let's look at some more of these. We proposed this back in '96 that there could be fossilized bacteria, including some very tiny ones, and more recently we proposed some of this material could be fossilized appendages of bacteria. Now this is one that many of you have seen, where this is about 800 nanometers, 0.8 of a micron in length. Is this a microbe? We don't know. It may not be, but it certainly has that appearance. Now, here are some things that we're more certain were caused by microbes. We have some chemistry on these. These little round mounds here in Nakhla were formed in a crack sequence. This is a calcium phosphate apatite crystal, but these things are typical of crystallization caused by individual microbes, and I'll show you some more of those. Again, here's some little ones on the order of 1 micron in size. These are little fossilized balls, which we think could be very well fossilized microbes. Let's compare these to some things that we know are fossils. We know that everything up here is a fossil because this is from the Columbia River basalt water in which the microbes grew and left these fossils. Same thing here. And these are all from the meteorites, and we're arguing that there's some morphological similarity. Doesn't mean they're the same thing at all. A few more, and a few more. The Columbia River basalt microbes in this column, and the Allen Hills one here, and the Nakhla here. Here's some of these little moundy things with essentially clay mineral precipitated on the surface. We think these are individual microbes which have coated themselves in clay minerals, in some cases in iron oxide. And this is a well-known phenomenon in terrestrial microbiology. There are many good examples of individual microbes precipitating coatings of minerals on the surface, including iron oxide is very typical in some clay minerals. We have some other things that we don't understand at all. We know this is calcium carbonate. It has a bit of a regular structure to it. It's about 3 micrometers long. And this is from Allen Hills. And then we see some similar things in another Mars meteorite from Egypt. We see similar things, again, calcium carbonate. Are these biogenic or not? We just don't know, but it's interesting that the same form, one is found in an Antarctic meteorite, the other is found in a meteorite from Egypt, but they're both from Mars. That leads us to suspect these are truly Martian, not contamination, but we don't know what they are. There are biofilms in some of the Mars meteorites. Biofilms are when colonies of microbes appear to develop and generate polysaccharide or essentially slime that glues them to the surface and keeps them together as a colony. This biofilm serves a very important purpose, which is to control the microenvironment in which the microbe is growing. And they can actually change the pH and the amount of salt, for example, inside that biofilm. It's like a little shelter. Back to NOCLA. This is one of the biggest ones that we've seen. We think that these are all possibly fossil microbes. This one I'm about to show you a chemical analysis of. This is with an energy dispersive spectrometer. And basically, it's hard to read the slide, but basically, this is that big oval-shaped feature, and this is the substrate around it. And notice that it's highly enriched in iron. It's got about twice as much iron as the substrate. And furthermore, it's got manganese in it, whereas the substrate had no manganese. The other elements are similar. So what does this mean? Composition rich in iron and rich in manganese. This is a typical fossilized coating. It's what happens when microbes become fossils. Just to show you a couple more pictures of things that we're sure are fossils. No question. These are iron baskets, which are individual cells which have coated themselves in iron, and then the cellular materials decayed away, leaving a basket, a lacy open basket. And these are various fragments of bacteria. And then this is a series of molds in NOCLA where perhaps bacteria were once in the rock and have decayed away. These are clay minerals, water rich, and these may be residue of the bacteria. We don't know. We're still trying to analyze those. All right, in summary then, we found a lot of fossil-like forms. We don't quite know. We have a very difficult time proving that they're microbes, but they are certainly consistent in morphology and chemistry with known microbe features from Earth. Organic carbon, I mentioned, I come back to. Yes, there is organic carbon in here, and we first reported that using our laser lab. This is Simon Clement from Stanford, who was co-author on the first paper, and he is able to use this laser mass spectrometer, and he showed that there were organic compounds in Allan Hills, shown here. And furthermore, they were concentrated in the carbonate rims, those Oreo cookie rims. The dark part, that's where the organics were. And here's outside the carbonates, and here's in the interior. There's a little more in the interior, not much outside. Also, he showed that these organic compounds, as you got close to the surface, they faded away. As you got close to the fusion crust, they faded away. There were none on the exterior surface of the meteorite. This is not Antarctic contamination. We also analyzed the ice in Antarctica. Allan Hills ice melted a big chunk of it, had zero organic polycyclic hydrocarbons, PAHs, in it. These are clearly Martian. That was a big controversy for a couple of years. I think everybody's given up on that controversy and agreed that these are truly Martian. And now we've started on some of the other meteorites. This is the NOCLA, and it also has polycyclic hydrocarbons. So to summarize, there's a lot of literature now showing that there is organic carbon on Mars. So don't let anybody tell you differently. There is organic carbon there, and it is from Mars. Then I'm going to finish up here with a discussion of the magnetites. We're back at the carbonate globules now. And if you look with an electron microscope, a transmission electron microscope, at the carbonates, you see these little square things. These are magnetite, iron oxide minerals embedded in the carbonate. Now, on Earth, there are really two kinds of magnetites. There's magnetite formed in rocks, and there's magnetite formed in bacteria. And that's about it. Now, why would bacteria form magnetite? They use it as a compass needle. Basically, the line of magnetite enables them to sense direction, just like a compass needle. Why would they want to do that? Because they make their living in this zone here, which is the oxic zone, anoxic zone transition region. They like to live in this area here because that's where these redox reactions are easiest to take place more easily. These are the magnetic lines of force, and these are the little compass needles in bacteria. They tend to line up with the magnetic lines of force, and then the bacteria can essentially find those zones by swimming up and down those magnetic lines of force. Here are some of them, again, from a known bacterium. This shows how there's some difference in the ones in the southern hemisphere from the northern hemisphere, but in every case they use the magnetic field as an up-down indicator, and that eliminates a random three-dimensional random walk. It turns it into a one-dimensional random walk, and it gives them a lot of advantages in finding these zones where they make a living. This is simply to show that the little magnets here are a certain size. They're called single domain size, and that's where the magnets are the most efficient. And these are actually the measured ones. 90% of the measured ones from a known magnetotactic bacteria and from the Allen Hills one fit in that circle, and that's right where they ought to be. Just to give you an idea on how tiny these magnetites are, you could line up 1,000 of them over the width of your hair. And I'll very briefly mention this. We have used transmission electron microscope to get the exact shape of these crystals. This simply shows how that works in the TEM. You basically see the projection, and even with a cube you can make a projection that is hexagonal or square or even rectangular by simply rotating the cube around. So that's what you have to do in the electron microscope to get the true shape. You have to make a lot of different views with a lot of rotations. It's just like a CAT scan, like a medical CAT scan. And we've been doing that. And we have described the shape of these magnetites exactly as well as we can, and it is it's an incredibly difficult thing to do, but we have and other groups have worked on the shape of these. And what we find, in short, is that these magnetites from known magnetotactic bacteria on Earth are identical in shape and size to ones from the Mars meteorite. And on Earth, how do the Mars meteorites are able to essentially form these magnetites by having a membrane that limits the growth in one direction and causes them to grow another direction. And that's what we think is happening on Earth and maybe on Mars as well. The other interesting thing is that on Earth we know they form little chains, and other groups have looked for chains in Allen Hills. And here's an example of maybe chains. They're not very well preserved. We conclude, as do some others, that there's no inorganic process that can produce these magnetites. Others have tried and they've not succeeded. They think they've produced them, but we can show they're not the same. And then finally, I'll just show you a new technique which we started using called focused ion beam milling. We can take a sample such as a carbonate here, and we can cut little slots in it, and I'll show you how that works. Here is an ion beam has come down and caught a little slot here. This is a platinum coating that is left behind, and as we see here, this region here is being hollowed out, and then here's what's left, this little platinum bridge, and this is what we're interested in, this little slice here. We reach down with a very tiny rod and essentially glue the rod to the top of that, and then we can lift this out. We lift it straight up, and here it is, lifted out of the rock, and then we move that flat plate to a electron microscope grid and glue it down to the grid. Here it is. And then we can look at it through the thinness of it, and we see things like this. This is truly the best way to slice things up, to look at them in detail with an electron microscope. And we see things like possible fluid inclusions in this, which are typical for terrestrial carbonates. Well, and to finish up, we conclude that many features can be made by microbes. It's still a controversial hypothesis, but it has not been disproved in any way. And we had 4 lines of evidence originally. Every one of those 4 lines of evidence is still, after 8 years of research, mostly people trying to shoot us down, all 4 lines of evidence still stand. So I'm going to quit with that, and I'll just to remind myself here. You can have questions after we're both through.
I know you're ready to ask Dave questions, but just hang on to them. What a wonderful time to be studying the red planet Mars. We presently have 5 spacecraft on Mars that are operating, returning data. Unbelievable. We have 2 on the surface and 3 in orbit about the planet. And what you're going to see today, I'm going to give you a quick run through. And there's an exciting new perspective of the red planet between not only the 2 rovers that are running around, but the 3 spacecraft which are in orbit about Mars. Mars is a fascinating place. We always wonder why Mars. Well, it's the only planet we have in our solar system that the conditions could conceivably be likely that life might be there. It has inspired humans since it first started being observed, and it's something that our youth can relate to very clearly. And one thing that we must remember, Mars is a big place. Even though the planet is smaller in size, the surface area of Mars is equal to the land area of the Earth. So just stop and think of all the exciting places on land on the Earth that you can go and look at. Here we have a planet whose surface is equal to that. So we're only looking at it at a few tiny hundreds or thousands of a percent of an area. So there's many vistas that are yet to be observed. We got our first image of the surface of Mars from the Mariner 4 spacecraft, which was in 1994. And some of the images were very fuzzy and hazy, and essentially everybody was blah, thought about the planet. And then image number 11 came back and showed us features that reminded us of our near neighbor, the moon. And so here was our first image of the planet. We really began to look at the planet in 1976, when we were able to launch 2 spacecraft to Mars and land them on the surface. Here you see Carl Sagan standing by a full-scale model of the Viking lander. The purpose of the Viking, very clearly, was to go to Mars and seek the signatures of life, plus successfully try to get vehicles onto the surface of this planet. We saw a dynamic, interesting place, from a sand dune surface to a rocky surface at Viking 2 out on the Mee crater plain, but we were also able to see dynamic features like water frost in the mornings. Water, the key to life as we know it. But we had 5 instruments on Mars that were seeking life. We knew that the surface of Mars was one which was very hospitable. The ultraviolet radiation would destroy organic molecules. So we had to go beneath the surface to seek any conceivable organism should they be there. So we dug samples from the Earth, but we used the 5 different techniques that were on Viking. There's a camera. The camera was to look around and see if something was moving on the surface. And then we had an instrument that was the most sophisticated that could be built in 1976. And that was a gas chromatograph mass spectrometer. And it took samples of the soil inside and it heated it up under carbon dioxide and under hydrogen, depending on how you ran it, to temperatures that would hopefully get organic molecules off. At a detection level of 1 part per million, none was seen. So it was really, people were quite surprised that no organics. So they knew meteorites were falling onto the surface, but the gardening effect and the ultraviolet were probably destroying these organic components. But we had 3 metabolic experiments on board that hopefully would challenge some organism that would be there. One was the gas exchange, which would basically look for metabolism. Results were negative. And we had the pyrolytic release, where we hoped photosynthesis was type process was operating. That also gave negative release. And then we had one experiment called the labile release, which we added a nutrient or soup to the soil and waited to see if we could get something off of it, if we had the right, basically, soup that the organism would like. Its results were kind of inconclusive, because one way pre-mission, what it gave said we had something there. But yet, with the absence of the carbon and the organic from the GCMS, everybody said, oh, it's some active ingredient in the soil. So here we were in 1976, 77 time frame, that we were left with conclusions of no life. So 100 years after Schiaparelli's canals, in 1877, in 1977, we were left with a situation from Viking that we had an active planet with water vapor there, which was important for the clues of life. We had carbon dioxide atmosphere, and we had these so-called iron-rich clays or material. This would be a nice environment for organisms to be there. So we were left with this kind of conclusion at that point in time. An active, dynamic planet with an interesting atmosphere above the surface, with volcanoes the size of the state of New Mexico, river channels. So something had gone on in its past. Well, we looked at this, and we know what happened in 1984. The Allen Hills meteorite fell here on the Earth. And then in 1996, we did our work and reported it and got interested into the program again. At which time, the United States had a mission in work called the Pathfinder. Pathfinder was going to go to Mars and hopefully successfully have a vehicle that could move around the surface. It only moved about 20 to 30 meters, not very far. It went out and tried to do chemistry on the rocks. But it saw a landing site that suggested something moved from the left to the right. This is an area geologically that had been interpreted as floods probably moved through at one time in the history. So we had an interesting surface observation. But then, in 1999, we were able to get the Mars Global Surveyor in orbit about Mars, returning thousands of images. We began to see, through the seasons of a planet, active areas around the rims which appeared to have something moving down, like fluids moving down slope. And this gave us ideas that there were fluids beneath the surface that could come out upon heating and water would be released. Good conditions for life. But this mission was followed by the 2001 Mars Odyssey mission, which had an experiment on board that was to map the abundance of the protons or hydrogens on the surface of the planet. This is basically give us a map of water. And so what it was able to do is produce maps that showed the blue is the areas where there's greater amounts of hydrogen in the polar areas, as we knew, and then there were certain areas that were decreased in amounts of protons, as you see, the uplands areas of the southern highlands. And hopefully this would give us information about the distribution of water. So from this data, we began to get a feel that early in the history of the planet, it might have been warmer and wetter, so that 3.5 to 4 billion years ago, at the time that the Allen Hills meteorite was formed, water was abundant, moving around on the surface, and something had happened for this water to be lost and be removed. but beneath the surface may contain evidence of water along with the channels and all. So, with the excitement from the Allen Hills 84001 and the time frame that the Europeans were working on a mission called the Mars 96, which failed, the European community decided they wanted to have a mission to Mars. And they wanted to refly the Mars 96. Colin Pillinger, who was a colleague of mine who I've known since 1969, said if we're sending a spacecraft to Mars, let's put a lander on it and look for the signatures of life or the carbon chemistry that conceivably could be there. And through Colin's efforts, he single-handed pushed this through and got basically a lander on board this Mars 96 mission, which is called post-Mars 96, to be called the Mars Express. So there'd be a lander. And so the European Space Agency was going to become a community of spacefaring nations. With their Mars orbiter, which is actively in orbit about Mars today, and it was to have a lander called the Beagle. Unfortunately, the Beagle did not succeed. The mission was an outstanding and is an outstanding mission. It's returning data that complements that of the United States' missions. We're getting global mineral maps, global high-resolution imagery from the three-dimensional, which you'll see some of the images here for long when we look at Mars with a perspective. We have maps of the minerals, we maps basically the atmosphere, trace constituents in the atmosphere. The lander was looking for the signatures of life in the geochemistry. Unfortunately, it did not succeed. Colin's challenge was to take a laboratory of instruments of this size, shrink them to a mass of 5.5 kilograms, or about 11 to 12 pounds, and fitting inside a 0.8 meter diameter spacecraft. He succeeded. This is a portion of the 0.8 of a meter sphere, and he developed something that's called a gas analysis package. It was packaged in the Beagle lander. Here it is with the air shell getting ready to be attached. It was attached to the outside of the Mars Express spacecraft. Here's the Mars Express spacecraft with its folded panels, and this was placed into the housing for the Soyuz rocket, and it blasted off on June 2nd of 2003. The last we saw of the spacecraft was on December 19th of 2003 when it left its Mars Express going to the surface. There's Colin being congratulated by Prince Andrew. And there's Everett right here. So we hoped to go to the surface. We did not succeed. What we think happened is the weather system moved across. The atmospheric pressure was less. The parachute systems opened later. We had all these sequences going closer to the surface. We made a crater. We're going to try again. So Mars is an active place. But the Mars Express cameras are revealing an interesting, fascinating place. From our perspective of the largest volcano in the solar system, Olympus Mons, we were able to see the summit crater, looking at it directly overhead. This is the size of the state of Connecticut. Now we're going to focus on an area right over here, which is the size of the city of Houston. The city of Houston would lie under that landslide. Interesting perspective looking at Mars from the angle as our human eyeballs would look at it should we be in orbit. Here's an image that has a stretch. The vertical has been exaggerated, but it's a fascinating history of geological events, from material coming down here, ponding here, and eventually coming out and filling in this basin. One end of the large canyon, equal to the size of the distance in the United States from the west coast to the east coast. One end of it, the Valles Marineris. Now, we're going to focus on 2 or 3 areas, on the water, the ice glaciers, and the volcanism. Here's one corner of Olympus Mons, and we're going to be looking at this little eastern corner. And you see up here, there's apparently ice has been here and has moved down slope. Looking at another area, you see these 2 features here. It looks like ice has moved down and flowed like a giant waterfall, flowed down in this canyon. Massive amounts of fluids have moved down into this lower areas. Here you see the end results of glaciers. Glaciers have moved across the surface and left giant striations as the ice moves, similar to what we see up in the upper Midwest, the ice ages here in North America. And then you see the effects of fluids that have moved through these canyons. Let's look at the pole. The deposits in the pole are just fantastic. Here we're seeing in the North Pole, we're seeing basically the vertical relief, about 2-kilometer height cliffs. Near the edge, it's smooth, and it's hummocky-like terrain. Is this a mixture of ice and volcanic ash? Volcanic ash? Let's look at this. We thought Mars is dead. No volcanoes presently active. But look in this polar region, and you see these 4 little cinder cones. These are relatively young. When we say relatively young, we're talking 2 million years probably, based upon the number of how few crater counts are there.
Sorry, I got a quick question. Are these, what we're looking at, are these images derived from
Mars? No. These are visual images from the high-resolution stereo camera that's on the Mars Express. This cinder cone right here is 600 meters tall. And there is the pit in the center where the ash is blown out. These are amazing features to be found in polar regions of a planet. Mars is not dead. Here is ground fog, giant canyons. Again, another end of side canyon of Valles Marineris. Mars is a fascinating place. Now, what about the chemistry and the composition of some of this material? The Mars Express has instruments which allow us to determine the composition of what is ice, water ice, and what is carbon dioxide frozen. Here in the southern polar cap area, you can map the CO2 frozen areas along with the frozen water ice. We're now getting this information, which before we did not have. We can also do mineral chemistry. Here are massive calcium sulfate deposits against the permanently north polar cap. This is from the French instrument, the Omega. We're beginning to get selected high-resolution mineral compositions within the areas of the planet. The atmosphere. We can do the composition of the Mars atmosphere and determine minor constituents that tell us about surface processes and perhaps organisms that may be there. We knew that the Mars atmosphere is mostly CO2 with nitrogen and argon. But it also had about 10 to 20 parts per billion by volume methane. Methane? Methane shouldn't be present on Mars because after 340 years, the UV radiation should destroy it by photodissociation. But the planetary Fourier spectrometer on board the Mars Express were able to measure this. We had 2 previous telescopic observations of methane abundances in the Mars atmosphere, and they gave values that were essentially consistent in the 10 to 14 or 15 parts per billion by volume. But with the instrument on board the Mars Express, we were able to get this global number of 10 to 15 or 10 to 13. But we're also able to see variations in the methane in the longitudinal area and with different latitudes on the planet. And it's also correlated with water. Greater amounts of water, greater amounts of methane. Could methane be a byproduct of organisms? Possibly. So what we saw was spectral information that contained a methane band. And this varied in abundances as you go up and down the planet with certain basins. And it correlated exactly with 3 of the large basins on the planet. So the hypothesis is where do you get the methane? The methane on Earth, we know, is primarily from livestock or termites. It also can be from peat bogs or landfill. Or it's beneath the surface in oil deposits. So you have 2 sources, abiotic from inorganic processes, and you'd say volcanic, the surface is coming out, you'd see a heat signature. None has been seen with any thermal instruments. What about meteoritic or cometary infall? You do the calculations, they're only about 2 or 4%, way below what you'd expect. What's contributing to methane? Well, possibly from methane in the atmosphere is from bacteria as a byproduct of methanogenic bacteria. And then we see the water. Water requires life. We know that the carbon in the Martian meteorites is reduced carbon. And its isotopic composition is carbon 12 to 13 is about minus 15 to 18 per mil. This is a number that's in the area, in the range of biogenic activity. We see the magnetite in the Mars meteorites, perhaps magnetotactic bacteria. And the labile release from Viking, I think we still have to realized that that could be telling us something. Now, as we look at this, how can we determine this? Beagle, our instrument which we were going to send to the surface, had a mass spectrometer. It could given you the data on the carbon isotopic composition of the atmosphere, plus also that carbon in the rocks. So let's fly it again. Colin would love to do that. No opportunity in 2005 to carry it there. What about 2007? We have a polar lander going. Collins offered this to fly in the 2009 opportunity. But the Office of Space Science and NASA said, no, we do not want to carry it. We're going to carry our Mars Science Lab. But perhaps the European Space Agency has their ExoMars or Aurora program, or whatever they call it. They have something in 2009 or 2011. Well, I think a perfect opportunity would be a minor atmosphere constituent mission where you could put a spectrometer in the atmosphere about Mars and get information about minor constituents, plus put a Beagle-like payload at one or two spots on the surface and get the baseline studies at the ground surface. This would give you really neat data. So the gas analysis package is the only flight-qualified life detection package we have. The United States program, as we have, has been one is built upon follow the water. The water, as we know, is a key ingredient for life. It also assists with the climate and the geology. And if we ever have humans going to permanency in space, we need to know the presence of water. Where is it, where it's located, how much, and the amounts and form. So we'll look at these parameters. And this is what was used to design the 2003-4 Mars rovers, Mars exploration rovers. Opportunity and Spirit are there to basically determine the climatic, water, and geology of the planet. They're acting as a geologist on the surface. But they're returning outstanding, spectacular data from two sites. From the three instruments we have in orbit, the supplemental data that's obtained from Gusev and at the Mariani site really is giving us really neat data on the surface composition of the planet. I'd like to lead you through some of this by going through the recent data that's been downloaded. In fact, some of it just came in yesterday. If we look at the first landing site, the Spirit site in Gusev Crater, you remember it's in a crater which material was thought to be brought down to this with water and left this delta-like deposit in here and filled this basin with water at one time. So we wanted to look at water alteration processes. And when we landed on the plains, it was flat, barren, desolate. They wanted to get away from this spot and head off to the hills. After the landing, from the tracks you see here, from the landing pad, you can see these from orbit. The lander, here's where they go, up, looked in the crater, and headed off. The rover at the time the image was taken was here, and then they're going to head off to the hills at the bottom. We have no trenching tool, but we can spin the wheels and dig beneath the surface, just like a hot rod. When you see these ejecta blanket debris, material scattered out. But as we looked in Bonneville Crater, the team decided, let's get to the hills. They continued on, going up to the Columbia Hills, which is the higher the elevation the team thought they could get to. And here you can see the path. It's not straightforward because you come to a point and you find there's boulders or a small depression or a high population of rocks, and you have to work your way around. We have two colleagues down at the Johnson Space Center that are working with the rovers. One of them is the actual rover driver. He thought he's only going to be working about 2 months or 3 months. He's getting tired after a year and a half, but it's fun science. So going on up the hill, unusual material started to be found as it increased in elevation. We found these rocks called pot of gold. You see this one, these appear to be the remnants of the surface alterations of rocks, where the rocks might have been soft and eroded away, leaving this crust of some weather alteration product. But in pot of gold in particular, when you look at it, you saw these little tentacles sticking out, these little knobs, and you look at them closer with a microscopic imager on the vehicle, you were saying, what is this? Well, they could do chemistry from the composition of the nature of the iron and found it's the mineral hematite, which is the red trace here, and this is formed from oxidizing conditions and abundance of water. Found our presence of water alteration products. And then they have the tool that's called the rock abrasive tool, or the RAT, and they can basically dig into a rock about 1 to 2 centimeters, or they can just lightly brush the surface. And they can then stick their analytical instruments here and determine the composition. And one of the interesting things they found by brushing the rock is the abundance of minerals, elements of sulfur and chlorine and bromine, exactly those like Dave was talking about in the alteration products that are observed in the Mars meteorites. Here we see these abundance of these elements, which are typically the salts that are produced in the evaporite solutions. And you can make a plot of the bromine concentration that was observed versus the chlorine, and you find they lie along this line. If you plot seawater, evaporate seawater, you get this abundance up here. And you see that these areas that have been brushed with this rock are enriched in their bromine and chlorine abundances. Clearly we're in an area that we're seeing the coatings of these rocks are from enrichments in the halogens, from evaporated fluids that were in this area. Exactly what the model was of why we went to this site. Well, going on up after the solar conjunction where we couldn't communicate with the spacecraft because we had Mars, the Sun, and the Earth in a line, we couldn't communicate for about 11 days. So going on up the hill, we stopped, and this is something that came down 2 days ago. These are dust devils moving. You'll see in one particular image there are 5 separate dust devils out here moving.
Can you give us an idea of what sort of range we're looking at?
It's tough. This is just like on a hill looking out into a valley. But you see these things moving. And they have both hazardous properties and beneficial properties. And let me show you how beneficial. As the rovers have been on the surface, their solar panels are beginning covered with the dust. And they were covering them up. And our power production started going down. But we had a dust devil go by. Here we were before the dust devil covered. And here's after the dust devil came by. And the magic duster operated. And look how shiny we are, ready to begin. Wonderful. It could not have been better timed because the rover was getting ready to go up the hill. So now we could have more power available to us for climbing and doing the science operations. So there is hazardous if you're human wandering around, but there are beneficial characteristics. So you got to plan your activity.
How big would those dust devils be? Are they huge?
They move between 15 and 24 miles per hour when they come by. They would be, if I was out there in a spacesuit and I would see one coming, I'd try to go the other direction. They have produced damage to the lenses of the spacecraft, of the rovers. They've left either material deposited on them or they have damaged a lens. But they're there. So as we sit on the top of a hill and look across the Gusev crater, in the distance, you can actually see the rim. And this varies how far this is. I think it's probably about 40 to 60 kilometers away. But what happens is it's not there every day because the dust devils change the opacity of the atmosphere. And so some days you see it, some days you don't. So looking back where we've climbed, we're continuing going up to the top, trying to get up to the hill, up here to look around. Geologies began to appear. Nice outcrops, overlooks for the geologists. A surprise, the presence of almost pure magnesium sulfate hydrate, one of the minerals that we found in the Mars meteorites in the cracks. So there's connections here. This is from probably evaporation of a previous sea. The nice cross bedding that is obvious in the contact across here. Geologist's dream. Now, the Gusev site, we're heading up the hill. The second rover landed in an area in the Mariani Polynesian. The Mariani site was one which had been mapped before for enrichments in a mineral called hematite, abundance of water. And so it was directly targeted to this area. And that's why it went there. It landed, bounced around, and lo and behold, after 13 to 18 bounces, it ended up in a small crater. A planetary hole-in-one. And as they looked out, they saw bedrock instantly in their first field of view. A geologist's dream. They've never thought they could see this. But as they looked out, they began to look at these layered rocks. And in the rocks, there were certain little features of these spheres. And this was a puzzle. So they began to look at this closer, and in the striations of the rocks, they could be reproduced here on the Earth if you had slow-moving fluids that were moving around 1 to 4 miles per hour, like a very slow meandering stream that left its precipitants behind. And it could, on Earth, you could produce textures like this, similar to what's seen here in this outcrop. And these spheres that are in presence, which are the composition of them, was beginning to puzzle people. But what was the base rocks? So they were able to drill, stick their X-ray spectrometer and Mossfire instrument in, and they found they were altered sulfates, a sulfate called jarosite, which is a sodium, potassium, and other mineral substitute, iron sulfate hydrate. And this is one of the major mineral phases that's in this area, along with silicates. But these spheres had everybody puzzled. These were little round BB-sized features. They were scattered all around the surface in the outcrops. And how do you determine the composition? Well, you couldn't pick up a handful of them yourself and analyze, but so they used Mother Nature. Out on a rock, out here, there's a shallow depression. And you look at this, the berries were concentrated in this region. So they could do an analysis, put their instruments over here, do analysis of the rock, and then place their instruments above an area where the berries were. And subtract the background here from the data here, and you could get the composition. And what were they? Again, they were made up of the iron oxide hematite. Similar to the reason they mapped the site to go there. Now, after leaving the site where they landed, they wanted to go, off to observe a big nearby crater. They're heading to this crater, the Endurance Crater, which is observed in all the maps, and going up to the edge of it to look in. This is 200 meters across. This is about the third the size of Meteor Crater in Arizona. That is 0.8 of a mile across. This one is 200 meters across, so it's much smaller. So looking down in, you see the surface. What are these little spherical things? Again, these BBs, the blueberries, are all over the surface and down into the crater. Drive your rover down with solid wheels on a rock surface with BBs, you might slide some. So here's to scale what the rover will look on a surface called Burns Cliff. Burns is for Roger Burns, a geochemist from MIT that was a very outstanding scientist that did a lot of the early work on the nature of iron minerals. So the team mapped a path into the crater, and the different colors are how far it traversed each day. So in going down, looking down forward into the bottom of the crater, this is its path. Looking backwards, you see each of these little holes, there's 9 of them, where they were able to do sampling and chemistry to be able to let Mother Nature dig this hole with the crater, and then they were able to analyze the chemistry with depth going into the crater. They got to the bottom, they saw these sand dunes. They were very brave inside. They didn't want to drive a rover up or into these. They might get it stuck and it'd be the last they would see. Well, we'll see what Faith had to deliver a little later. So they headed out of the crater, headed off out across the terrain. As they went by where the heat shield had separated from the rover as it was delivered to Mars, and this is where the heat shield impacted, turned inside out, and was lying over here. A little further along, the most amazing object, an iron meteorite the size of a basketball, was sitting on the surface. We now have seen little small 6-inch diameter craters and 2-inch diameter craters where small objects are impacting the surface of Mars very, very recently. The winds have not covered them or altered. So it's an active, dynamic surface. So the rover was headed off from Endurance Crater down to visit an area called the Etched Terrain. But as it was going in an autonomous mode and in some days making as much as 600 to 700 meters a day, as fate would have it, they drove themselves into, these are crest of sand dunes. And the rover is stuck right here in this rim. The height difference of this crest coming across here and the bottom is around 20 inches. But what are they doing? Back to the old test bed. Here the rover is in test bed at JPL with material of the same texture, and they're driving it back they're going to be driving it back and forth to see the product, how to get it extracted. Very, very careful when you got a car of this price tag. Now, what other science is going on? Here is basically a solar eclipse by the satellite Phobos, moving by the sun. Weather on Mars, clouds. It's not all clear. At times, there are weather systems and clouds that are there. So what have we seen? We've seen an aqueous altered environment, that the waters have been there in the past. They've altered the rocks. We have coatings that are rich in bromine, chlorine, and sulfur. They're in both sites, and they're outcrops. And so this is neat. The mission was to head for water. They found the evidence of water. What about the life of the vehicles? Originally planned for 90 sols or 90 days. They're up to 462 and 443, I believe, today. Originally planned, hopefully, 600 meters. They've gone in excess of 4,600 on one of them and 600 on the other. They've gone in excess of 2,700. Almost 70,000 images have been returned, and you can view every one of them on the web. Now, what are their status? 26 hours. A sol is 26 hours, roughly. Okay, Spirit is showing signs of age. One wheel is having its difficulties. They drive it forward and they drive it backwards, and sometimes they drag the wheel. There's lubricant problems. So the power drainage on one wheel it goes up and down. They'll continue to climb into the Columbia Hills. Opportunity landed with a heater stuck. It drained the batteries, but they went into something called deep sleep, where they turn the batteries off at night and give them more power and they recharge. But it's currently stuck in a sandbank, but they probably have it extracted. Both of the panels have been cleaned, and they probably last another year. Now, let's refly Beagle, or a similar type of Beagle, to go to look for the minor species in the atmosphere. And Darwin says, let's do it. This is a man from Houston that portrays Charles Darwin in the classroom. I don't know, any of you ever met him or seen him? He's really neat. I mean, he moves himself back into 1830s and 1840s. And he talks about his voyages. Amazing, individual in the classroom. Now, Colin wants to refly a mission to Mars. And he's proposed this as basically a mission that ESA itself wants to have. They want to have a lander, they want to put something on the surface, and they want to successfully get it there. So what he's done is gone out and brought the geophysical community in with the life science community to recover the science lost from Beagle. And this is basically a network geophysical mission, and hopefully go into some program that it'll have. And the science aim are just outstanding. You look at the carbon, the geochemical cycles, go after the methane, its isotopic composition. Because of the isotopic composition, you can determine if that's from bugs or if that's from geology. That's very important, and that's the only way you can do it, plus other properties. And what he's come up with is basically a lander that instead of the spheres for bouncing, it's soft airbags. The airbags will slow it down. Retro rockets will slow it down, the parachutes, and it'll bounce on the airbags and not go bouncing around. And once it's landed, a small rover of about basically 0.8 of a meter or so will drive off either direction, set out a seismic package. A drill on the thing could drill a hole, put a heat flow probe in it, and they could get the science. If you want a more advanced one, you can go down a couple meters and go for the water table. Now, that's what he would like to do. Europe is debating what are they going to do with this. They have this Aurora program or ExoMars program, and everybody wants to, quote, study it more. We've heard that before. If you do that, you won't accomplish anything. United States mission, where are we headed? With the 5 spacecraft in Mars presently, and 4 of them in the United States, we have a mission that's going to be launched in August called the Mars Reconnaissance Orbiter, followed in something in 2007 and a 2009 type mission. Well, let's look at the 2005. This August we'll launch this orbiter with high-resolution imaging capability, but extremely high data rate capability. We can get more data back from the orbits of Mars. We can use the other vehicles to send data to it, and then it will transmit it back in a higher data rate. Now, 2007 is a reflight, basically, of the Mars Polar Lander. And this is called the Phoenix out of University of Arizona, and basically look at the aqueous geochemistry of Mars and the nature of the water at the ice at the poles. Now, the 09 opportunity. It originally was stated that we would have a Mars Science Lab. This appears to possibly be slipped to 2011. But this is a mission that the PIs have already been chosen. It's basically searching not only for the water, but also the chemistry and some of the biological signatures, hopefully. And then the ultimate one, as Dave and I would like to have, is a mission that we can return a piece of Mars back to a lab here on the Earth. When is that going to happen? Probably beyond my scientific lifetime. But hopefully we can train the youth to work on this, the excitement. But we need to know where the samples are from their context. Not just have samples that we don't know where they're from on the planet, but know exactly where they're from and collected for a specific reason. Now, the President has said we have basically, a spirit of discovery. We're looking at sending humans back to the moon and onto Mars. This is really neat because these robotic missions we have and the missions that they're going to be working on are trailblazers for the humans. And these will lead eventually to the lunar outpost and hopefully then on to Mars. And when this will happen, it'll be 2020, 2030 time frame. But the important thing of all this is we got to remember, we got to leave the spirit of exploration in the interest of science in our youth, because they're the ones that are going to be carrying this program out. Dave and I are going to be retired. We're going to be sitting back and saying, go, 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 as we hit our cane or something on the chair as we watch the rocket go up or the guys go over the hill looking at something. But the youth of our nation and those in college are going to be the first geologists and the scientists and the mission planners that are doing this. And this we got to remember, and we got to instill this excitement into these people. As NASA's vision is one that says, improve life here, to extend life there and to find life beyond. We might have tried to do it and find the signatures of biogenic activity in the Mars meteorite or the missions we have ongoing now. But it's a truly exciting time of what's going on in the Mars arena. 5 spacecraft operating, another one to be launched in August. I would have never thought I'd see 5 spacecraft at Mars and 6 spacecraft at Mars at one time. But it's truly an excitement period. Europeans are in the game to play for sure. They are major players. They're doing great science. And just stand back because the Mars Express is going to be returning some outstanding data along with the missions which we have. I know this has taken a while. We've shown you a lot of images over a period, but I hope we haven't bored you. Dave and I will be happy to answer questions. This meteorite is a piece of the Rosetta Stone. This is the Rosetta Stone that allowed us to prove that we had rocks from Mars. This is a piece of 79001. And as you look at it later when you leave, it's a fascinating rock and all. Questions?
I think it said, the slide said EETA 7901. What is EETA?
We put a nomenclature system on samples. EET is an elephant moraine. 79 is the year it was collected. The 001, it's the first sample processed back in the laboratory here in Houston. Allen Hills 84001. ALH is for Allen Hills, the moniker. 84 is collected in 84. 001, the first sample processed in the laboratory. It's not the first sample picked up in that field season. Because the team looks at it and says, this is a goodie. As soon as you get it back, look at it as soon as you can. And the field team, as those of us who participated, lets the team know. This is a part of a soccer-sized ball that the team I was on in 1979 collected the rock.
How would you get a rock from Mars to Earth? How does it get here?
Okay, it's a good question. Question, how do you get a rock from Mars to the Earth? First, you have to have some event to occur to cause the sample to escape the gravitational field of the planet that's holding it down. You can have an impact on a planet or body of Mars, and if the escape velocity that's transferred into that soil sample is greater than 5.7 kilometers per second, it will escape the gravitational field of Mars. Now, everybody said, now, really? You don't want it to hit this way. You want your projectile coming in to come in at an angle where the energy is in and it accelerates the material out in front of you. That leaves you an elliptical crater, not a circular crater. Now, our elliptical crater is about Mars. This velocity is only 3 times that of a 30-06 deer rifle. So those of you who hunters go out and you pop Bambi's mother, you're using about 1.7, 1.8 kilometers a second. A meteoroid passes through the Mars atmosphere, which is very thin. It will impinge enough energy for it to go off. It'll travel in space for a period of time until the gravitational attraction of some body attracts it and it falls in. This model was out there in the early 70s, and the geophysicists said, you can't do that to get material from the moon. Well, we had a rock discovered in Western Australia that was a lunar sample. A sample in hand will make a lot of geophysicists go back and redo their calculations. This lunar rock was lying on the Western Australian desert and it was picked up. It had characteristics of some of the Apollo samples. And we analyzed it, trapped gases, chemistry, is another sample of the moon. Geophysicists go out and calculate and say, oh yeah, you can kick material off the moon if you bring it in at a low angle and kick it off. This is why we have 28 or so lunar meteorites here on the Earth now. They've been found because they've been kicked off the moon, and the 35 samples from Mars.
So you have a reverse problem here. You have a spacecraft with human beings full of bacteria inside a chamber on Mars. They even go out and have their spacesuits, heaven forbid, some accident and their suit is torn. Now you've blown millions or billions of firstly bacteria all over Mars. They might even find some of this water and sprout and thrive. Once something like that's happened, how would you ever know whether life originated on Mars or whether we just spilled a lot of bacteria all over the place?
That's a real concern, and NASA has a planetary protection officer, and his sole purpose is to keep bacteria from ever going to Mars and vice versa. The saving grace is that the UV there would probably kill any bacteria that simply fell onto the surface of Mars in a very short time. But we don't know that for sure, and we don't know that there are not moist places where a bacteria might just take off. So that's a problem. There are a lot of people looking at that problem.
About the magnetosensing bacteria from the fossils you found from the Mars meteorites, how does the magnetic field and magnetic field lines of Mars compare to the ones here?
That's a good question. When we first proposed that those might be fossils from magnetotactic bacteria, everybody laughed because they said Mars had no magnetic field at all. In fact, it does not have a field today, but the Mars orbiter has found some magnetized rocks, big areas of rocks on Mars, which indicate that it had a very strong magnetic field early on, and which has decayed away. But those rocks are still around. So the answer is that there was a very healthy magnetic field, perhaps stronger than the Earth, early on. Then around 3.9 or so, that died away, but there's still some left just because of those magnetized rocks. 3.9 billion years ago. Yeah.
Philosophical question. Assume we found life today in smaller forms. We're going to intervene with its evolution. To go there.
If we find life on Mars, will we intervene? Is that your question?
Its own natural evolution.
I don't quite understand your question.
If we find life in Mars, assume the source of the methane there today is coming from some activity of life. Not seeing just the fossils of it, but the reality is there. Are we still continue to send equipment from here, people to
that-
when it's evolution?
That has been a matter of some debate, and there's one school of thought that says don't mess up Mars, don't if it has an ecosystem, study it, but don't perturb it. But it's not clear how you study it very much without perturbing it. I think initially we've already sent a lot of hardware to Mars, as you've seen. Nobody thinks that has harmed Mars so far. I think the next step is to bring back some real Mars sample and we'll tell whether there's a live system, I think, if we get the right sample. And then what do you do? If there's really microbial life on Mars, what do you do? I think you have to establish some very careful guidelines to keep from screwing it up. At the same time, you have to study it. It'll be the most astonishing scientific discovery will be to take Mars life, look at the DNA, look at the evolutionary sequence, see what has gone on, compare it to Earth. We'll learn an incredible amount from doing that. We cannot miss that opportunity.
We have, of the 35 samples from Mars we have now, they're all subsurface samples from essentially a half a kilometer to 100 meters depth. They're not the surface samples. The question is, why do you not have a surface sample? I personally think they're not strong enough to survive entry in the Earth's atmosphere or loss being kicked off the surface of Mars. But we've had Martian materials already brought here. Early in the history of the Earth, we had large bombardments going on. We might have had free exchange of materials in the inner solar system. I think we have to keep our eyes open for that. We would love to know the nature of the carbon on Mars. We do not know the complete geochemistry cycle of carbon on Mars. What are the reservoirs of carbon on Mars? And what's its isotopic composition? That would help us a lot. And then if we could go in and break it down to individual organic molecules, DNA if it's there, amino acids. Right? There's some data even that hints that one of the Mars meteorites, the Nakhla, which is a fresh fall, contains some amino acids that are non-terrestrial amino acids.
When you use the word life, you imply, I guess, that it's Earth-like life or carbon-based life. Is that the case?
Yeah, and that's a good question, because what if it's something totally different we're not familiar with? But our feeling is that we have to start with something we know, and we know what we know about Earth life. So we have to assume initially that it'll be similar somehow to Earth life with DNA and carbon-based and not silicon-based. And I know that there are people who have written scholarly papers suggesting other kinds of life that are just not based on the reactions that we're familiar with. I personally don't think that's very likely, and so I think we should stick to what we know and go from there.
The silicon atom is not one that would be conducive to develop life from. The bonding it just doesn't work. It's a fundamental chemistry problem.
Free exchange of material in the early period of Martian existence. What do you think the possibility is that we're all Martians? I mean, if you get DNA back, you could maybe have the answer.
I think the abundance of carbon at the start of our solar system was from the same reservoir, and it got separated out, Mars and the Earth. Now, how far back do you want to go? I know the oxygen is different from the Earth and the Moon. I mean, Earth and Mars, but the carbon, I think it's possible. But I don't know how you would determine that until we understand things better.
I think that it's pretty clear that there's been an exchange of meteorites back and forth since the very, very earliest days of the Earth. And whether life started on Mars and got transported to Earth or vice versa, I don't know that we'll ever be able to tell that if we find life on Mars, which I'm sure we will. But I think that the third possibility is that life comes from somewhere else, neither Earth or Mars, and falls down on both planets. And I don't know how we'll solve that one either.
Well, we're going to have a reception afterwards, so I think if there's any more questions, we could follow them up outside. So, thank you both.
Fun. Thank you.
Thank you, Neil. Glad you were.